Okay, folks, so we're going to kick off this session, millimeter wave 5G, 6G packaging. My name is Joe Ionati. I'm a senior principal engineer at GE Research Center. Our first speaker is Shelby Nelson from Mosaic Microsystems. The title of the talk is Thin Glass Interposers for Millimeter Wave Packaging Applications. Dr. Shelby Nelson is Chief Technology Officer and co-founder of Mosaic Microsystems. She's a semiconductor device physicist with broad industrial and academic research experience. She's worked at AT&T Bell Labs, IBM's T.J. Watson Research Center, Xerox Corporation, and Kodak Research Labs, and was the Claire Booth Luke Associate Professor of Physics at Colby College. She's authored over 40 journal articles and holds over 65 patents. So with that, I hand it over to Shelby.
Good morning. Thank you all for being such early risers. 8 o'clock seemed to come very early today after last night's lovely dinner. My name is Shelby Nelson, and I'm going to give something of a Mosaic-centric talk. We're a startup, as you will see, and I welcome you to the 10 o'clock talk by Vern Steiger. He's going to give, I think, something that's more of a more general view of glass. So you'll get a couple of opportunities to see glass today. So Mosaic was officially founded in 2016, but in the Shelby-centric universe, it really started in fall of 2017 when I came on board, and we got our clean room in 2019. So we're a relatively new startup. We're up to 12 employees. And what we do is make glass interposers. On the left, you can see here a transparent filter array with kind of a looming presence behind, showing you how transparent it is. And that's a picture of one of the bays of our clean room in Rochester, New York. So why glass? There's a lot of reasons people are actually interested in glass. From the millimeter wave regime, the biggest thing is it really is an insulator. It's not a semiconductor. We heard yesterday in the panel session, somebody was talking about the fact that really silicon interposers have their value, but there's a lot of other substrates out there, and glass is one that has that value for very low loss in the gigahertz frequency range. So in that sense, it actually beats silicon, which is a rare thing. Environmentally, one of the advantages of glass is that it's impermeable to moisture, and so its dielectric properties don't change with the environment. And that can be highly valuable, again, when you're highly sensitive to those dielectric properties. It's also high temperature compatible. Physical and mechanical aspects of glass, it's very smooth. That's one of the kind of exciting things about it. It's as smooth, can be as smooth as a silicon wafer. So you've got less than a nanometer roughness allows you to really develop high density interconnects. And that's an area that people are very interested in. And depending on the formulation of the glass, it can be formed in very large sheets, which makes it easy for panels, easy for scaling, and it's produced thin in some of those formulations. So what we're seeing is a lot of people are interested for advanced packaging in thin glass. So there's thick glass applications, and then there's some that are thin, and some of that is for the low latency, the short interconnects between front and back, and that form factor. But of course, there are challenges. Thin glass can be very flexible. It's transparent. So some people's sensors, machine sensors, don't see glass. And although there are temporary bonding solutions out there that we even use sometimes, most of those can't leverage the high temperatures and conditions that a lot of semiconductor processing wants to access. So Mosaic actually addresses those challenges. So one thing is that thin glass is actually really hard to ship. It is typically shipped in a coin stack with Tyvek separators. What that means is it arrives not in a semiconductor clean condition when you get it. So Mosaic actually cleans glass. We provide precision, fine pitch through glass vias. And that would be to our customer specification. And Mosaic is providing a void-free fill these days in-house as well. And then the key here is that we have this extremely robust temporary bond. And I've shown here a 300 millimeter, 100 micron thick piece of glass that is bonded to a silicon wafer, a 300 millimeter silicon wafer. And it looks, acts, and smells like a silicon wafer, right? You're back to that shiny round thing that we were talking about yesterday, which is what people are used to doing. And that the bond is the trick there. So I mentioned that the glass does not arrive semiconductor clean. This is just a bright light underneath a piece of glass, and you can see that's the light bouncing off particles. It's not nice. In this case below, this is just a test pattern of TGVs, some dense squares of TGVs, again, on incoming glass. So once we're done with it, though, we actually can see that the glass is really clean, and it's required for our very thin bond. It's required that it be particle free. We don't actually manage to clean the scratches; those stay, but we are particle free. And what that allows us to do is have a very particle free bond. So what I'm showing you here is our initial spec for ourselves was about a 1.5% of the area of the wafer. We wanted the bubbles to be less than that. So a very small particle can give rise to quite a visible bubble, optically easy to see bubble that may not actually be a problem for processing, but certainly is a PR problem. So we learned how to actually make sure that our bubble density stays very well below our spec. Oop, what the heck just happened here? And I just wanted to point out that this process, while we are primarily wafer focused so that these wafers can kind of integrate into people's current processes, we go all the way from 100 millimeter wafers to 300 millimeter wafers. The bond works fine on panels as well. Once you've bonded them, these things, again, can be shipped in a semiconductor clean vertical shipper, and that's quite an advantage. So I mentioned that we create the TGVs. We've worked very hard on making sure that we understand how to create different shaped vias. In some cases, a tapered via is advantaged for our customers. And you can see at the bottom here, a 3:1 aspect ratio via that has been filled with copper. The overburden is still in position. So what you're seeing there is the silicon handle down below, the glass wafer, and copper fill. There's the overburden. So now you've taken the thin glass with TGVs and you've created something that is the same to fill as, again, the industry sort of used to with TSVs. It's a blind fill. We can do very columnar vias, as you can see in the 4:1 aspect ratio via in the middle. And we also can do very narrow, deep, so aspect ratios up to 10:1. We've demonstrated. The trick, of course, as anybody knows who's tried to fill vias, is that those have to be void-free, and that is what we've developed, is a void-free fill. And these are over glass. We tend to concentrate on 100 millimeter glass up to 200 millimeters. We have dealt with glass that's thinner. As you get down to 50 micron thick, did I say millimeters? Yeah, I throw factors of 1,000 around like they're nothing. So we actually deal with 100 micron thick glass and up to 200 micron thick, which is the regime where a handle really makes a difference. By the time you get up to 300 micron thick glass, a handle is much more optional. It's easier to handle on that. And the vias that we've demonstrated so far range from about 10 to about 35. We find that the maximum of 35 micron via is advantaged from if you're going to fill it with copper, which has a high CTE. We find if you don't make the vias too large, then you don't end up with any cracking or any issues, even with thermal cycling. So we try to limit the size of the via. And we can do pitches down to about 3 times the via diameter. Okay, so the idea is this. So we clean and create the TGVs in the glass. We bond it. And then that bonded pair can go through whatever process. that our customers need. And then there's a mechanical debond at the end. And the nice thing about this bond is it's actually strong enough that, for instance, a CMP process, which provides plenty of shear, even grinding processes, which might be even worse than CMP, the bond is unfazed by that. So you can take here, this is a copper, the overburden after we filled vias, and this is the wafer after CMP. The bond is robust to over 400 degrees C. What I'm showing in the graph down here is a measured bond energy for a number of different temperature anneals. What you can see is that even above 400 degrees C, you're still at a bond energy of 300. If you compare that to a van der Waals bond, which is maybe on the order of about 100 millijoules per meter squared, this is strong enough to actually take you through whatever processing you want to do. So very temperature resistant. It's chemical resistant. You can throw it in acids, you can throw it in solvents, it doesn't matter. The wet processing is fine. I've mentioned the mechanical resistance, and we certainly do vacuum processing again and plasma processing. At the end of the process, you've got some kind of beautiful RDLs on your interposer. We put the beauty side down on a dicing tape and suck that onto a vacuum chuck. And then the handle is what is pried off in the mechanical debond. So the beauty wafer gets to stand still. I don't know if you can see, there's a debond front as a piece of fused silica is pulled off, the handle of it is pulled off the wafer there. One of the nice things is that our bond doesn't leave residue on the wafer. And we've checked this with XPS. What I'm showing here is a variety of elements that we were looking for. We checked the glass prior to bond, and then we debonded and checked it again. And there's a very slight variation in the carbon. That's within the noise of what we would see for a plasma cleaned piece of glass and one that has sat in the room for an hour. So it's basically about the amount of adventitious carbon that you expect on a piece of glass in the room. So there's basically no cleanup. And anybody who's paranoid about it can throw it in a 10-second oxygen plasma and then be guaranteed that's pristine glass again. What this means also is that, again, in a TSV, typically you would do a grinding process to reveal the backside of your via. In this case, we would do our post CMP anneals in situ on the handle. And then when we debond, the reveal is just the back of the glass is there. So we've done optical profilometry measurements to show that basically it's a very coplanar surface there within 50 nanometers. I'm going to try to get my factors of 1,000 right there. So it's a very simple backside reveal. So Mosaic does not make glass, just to be clear. We just handle glass. And so I took these pictures off the internet because that was where I could find them. Fused silica is grown in big pools. Display glass, such as Willow, this is a picture from Corning's website, is grown through a fusion process. And so this process on the right gives rise to wide, very long pieces of glass. And that sort of lends itself as you think about scaling. And that low alkali display glass. So sometimes I've heard it called alkali-free glass, and then sometimes I hear it low alkali. Bottom line is that glass is compatible, certainly with the back end of the line. I'm not sure if people want to put it in with their silicon transistors, but back end of the line, very compatible with fabs. And once you take a piece of glass that's been cut into a wafer and put it on a silicon wafer, then as this glass moves through a fab, even the chucks only see the silicon that they're used to seeing. So there's no contamination there. And so these are the main types of glass that Mosaic has concentrated on so far. We're open to others, but this has been mostly it. And so the wafers over here have to be cut out of the boule and then sliced like a silicon wafer. So people's application determines which glass they find to be the most appealing for their application. And certainly for millimeter wave things, the very low loss of fused silica is usually very appealing. But there are some times where the fact that there's a CTE match of the more display-like glasses to silicon can actually win the day, even though it's much lossier. So the modulus of those glasses is very similar to each other. The CTE is quite different. So of course, fused silica is 0.5, where the display glass has been tuned carefully by the Cornings and Schotts of the world to be close to 3.2. So very, very matched over a range to silicon. Dielectric constant and the loss tangent are the ones that can actually distinguish for various applications here. And we'll come back to, these are the numbers that we've been quoting for a long time. We got them out of the literature somewhere, and it's actually kind of interesting that they may or may not be correct. So that's kind of a background on Mosaic. One of the things I wanted to talk to you about is a project that we're participating in, which is an INEMI project for creating a reference material for characterizing dielectrics in the millimeter wave regime. It turns out that there are no standards there right now. And this is a follow-on project to one that came before. So basically the 5G materials characterization project basically said, without a traceable reference, it's really hard to let your engineers really understand what's the dielectric properties of your various materials that you need to use to build up interposers for millimeter wave applications. So this project that we're involved in now is working on creating a reference material. The project leads are Nate Orloff from NIST and Mike Hill from Intel. And the project lead from INEMI is Ermi Ray. So this was some of the motivation for this second project. This is data from that first project where you're looking at the dielectric constant and loss tangent of a piece of high purity fused silica. And what they did was they actually sent the same pieces on a round robin to be tested at a variety of labs. And in this case, they used the thickness that was measured by one of the companies rather than each company also measuring the thickness of the sample. So when they do these split ring resonator measurements, you need to know your dimensions very, very accurately. So there's a lot of ways to basically not be exact. So here we are with the same, did I just go? No, with the same substrates being measured with a 0.4% variation across different companies across that frequency range. Now, in the world that I live in, 0.4% variation tends to be like, in the world that NIST works in, and when you're trying to really get the permittivity measurements so that people's capacitors and interposers behave the way they should, that's a component that goes into a further calculation that can actually end up costing millions of dollars. So that's actually a big deal. So one of the things to notice that even with the scatter, we're looking at a 60 gigahertz measurement out here that's looking like it's even better than what I quoted before for high purity fused silica. So this is really a very nice low loss material. And I think out of this project, we're going to get, once there's a reference, we're going to get even nicer measurements. So as part of that first project, just for fun, the graduate students who's working with Nate Orloff also measured some of the willow glass. And because of the higher dielectric constant, and it was 150 and 200 micron thick glass, I guess that's thick for them. There were some odd measurements up at the highest frequencies, but it's kind of nice to see that really there's going to be some nice data on all kinds of materials as this project moves on. But so the plan is to provide a fused silica reference that the world can use. They will have kits that you can use to characterize your own equipment so that then when you use all the other materials that you have to characterize, obviously fused silica is not the only thing that you want to characterize. This is just the reference. And they want to create basically substrates that have some calibration features around the edges, some kind of coplanar waveguides and things, and then these reference materials that can go into the resonators. And the difficulty is that the requirements on TTV for this are very tight. So you want a thin material, sort of 150 microns or 100 micron thick, and you want it to be very tight TTV so that the thickness uncertainty is reduced. And if you do want to fabricate some of those structures around the edges, I have to say, you're going to find that a lot easier if you have a handle wafer. So in fact, what is pictured here is a reference sample that was made earlier with a handle. So it gives you the ability to handle that without a lot of problems. And so the point here is that Mosaic is actually providing very thin fused silica with very tight TTVs. And these are actually pretty remarkable numbers. This is a 150 millimeter wafer with a better than 0.2 micron TTV over the whole wafer. So we've sort of mapped it. And we can provide even 200 millimeter wafers. Over that whole wafer, the TTV is so much larger. But if you're cutting out those same size squares in any one square, the thickness variation is small enough so that they can use it for this reference material. Or at least they're proposing to explore that. Okay, so that was one aspect of millimeter wave related stuff that we're working on, which is the fused silica. There's another project that I just wanted to tell you about, which is for low loss, high gain, glass-based radar arrays. So we're working with the University of Florida, Professor Y.K. Yoon and Dan Otz. And Professor Yoon has been very active in this area of creating multi-layer structures that actually reduce the RF resistance relative to copper. If you're like me, you think, well, you're not going to do better than copper. But at radio frequencies, you can. So basically, having something like cobalt or nickel in with the copper alternating layers suppresses the eddy currents. And so in the 7 to 32 gigahertz regime, they've measured resistances of up to 50% less. And so what we're doing is, as part of the characterization before we go and make the actual radar arrays with this, is make some two-turn inductors to characterize the Q factor of these and verify that we're actually seeing the improvement with this low loss material. So you can see if you're into that kind of thing, you can see the dimensions of the material here, and in this case it was a 100 micron thick piece of glass. So the TGVs are part of that inductor loop. And these were fabricated on 100 millimeter wafers, because that seems to be what the university fabs often like to work on. And the work was done at Florida. And this is while it's still on a handle, and then we can release and flip and do the back side. So initial results from this are very promising. The comparison here in the graph is what are nominally identical to single ring. I think that actually two-turn inductors, one of them with copper and one of them with this multi-layer metaconductor, and you get a Q factor doubling. So that actually can be very interesting for some of the power amplifier applications where you actually want to have a low loss next to it. I think there's a lot of interesting things that are going to come out of that. So I have no idea what time it is. I have no idea if I've raced through this thing or if I'm slow, but basically what I hope I've demonstrated is that we actually have a very high yield approach to handling thin glass. And again, yesterday at the panel, somebody was talking about these round, shiny objects, which is what we're used to. We've kind of taken glass and we can, if we want, turn it into that round, shiny object that people are used to working with. And it allows that void-free fill, which again is an issue with SVs and TGVs. And I think what it's doing is helping make thin glass accessible to all of those growing 5G and 6G millimeter wave applications. As we like to say at Mosaic, the future is clear. Right. So what we've seen with fused silica is if you have a 35 micron via in fused silica and you take it up hot enough, you can like lose your hermeticity of the vias because the mismatch is even more. On the other hand, if you don't have to cycle up to 400 C, you may actually be fine, or if hermeticity is not your issue, you'll be fine. We haven't seen any cracking. With the willow glass, we've actually taken it filled vias, I guess 25 microns diameter up to 450 C for 90 minutes, cycled it twice, no cracks, no change in hermeticity. So. That's a really good question. So for those of you, if you didn't hear Joe, it was what's the batch to batch variability on fused silica? We haven't looked at that yet. I think that is part of the goal of this INEMI project because they want to know that all of the sets go out with sort of a calibrated, that it's calibrated. And by the way, if you are interested in this kind of calibrations, Nick Orloff at NIST would be delighted to talk to you, and I can give you his email address if you need it. Thank you.
Yeah, thanks a lot, Shelby. So our next speaker is Tom Rovere from Lockheed Martin. The title of his talk is Additive Manufacturing for Heterogeneous Integration Benefits and Challenges. Tom Rovere is a research scientist in Owego, New York. Over his 15-year career at Lockheed Martin, Tom has served in multiple positions, such as a reliability engineer, process engineer, is currently the RMS operations expert for advanced electronic assembly and repair. Tom's core responsibilities include research and development related to flexible hybrid electronics, printed electronics, antenna manufacturing, secure processing development, and reworking of BGA QFN package devices. Tom has earned multiple trade secret awards and serves as Owego's IPC representative and as an Empire chapter officer as VP of membership for the Surface Mount Technology Association. Tom graduated from Lehigh University in 2006 with a Bachelor of Science in Material Science and Engineering, and in 2015 earned a Master's of Science in the same field, Material Science and Engineering, from Binghamton University. So with that, I'll turn this over to Tom.
Thank you. All right, good morning, everybody. Welcome to Binghamton. So this is a little bit closer commute for me, so it's a lot better to come here than to go to work. So thank you for having me. I'll kind of go back a little bit over kind of my career here. Just for you guys, I've been doing this for about 15 years in circuit card manufacturing. I've heard a lot of talk about the valley of death that people talk about. That's kind of the area I live in at work. You know, I do a lot of prototyping and, you know, getting products off, you know, from, you know, low rate production to production. So that's kind of my expertise is in that area. I kind of serve as the liaison between design and manufacturing. A lot of times the manufacturer or the design engineers come to me and are always asking me, you know, how tight can we bring things together? Can I use this, you know, bare die component and put it on the circuit board? In most cases, I have to say, yeah, you can do it, and, you know, hope for the best and figure it out later. But, you know, so that's kind of where this presentation came about, is trying to educate people on, you know, the benefits of this additive technology. That's kind of a new technology, and and also highlight the challenges, because I think I see a lot of presentations that are sometimes very optimistic. You know, hey, we're gonna stick this board in a machine, and it's gonna come out and it's gonna be a fully functional, you know, completely realized board. And I don't think that's ever the case. But I also see presentations that are very pessimistic about the technology. So I'm trying to, bridge the gap and kind of show both those areas of where we are, what we are actually capable of, and help people understand what those are so that they can, produce ideas capable of being produced. Let's jump. Last thing I'll mention here too is I have a lot of photos here, compliments of several companies: Optimec, Sunray Scientific, Georgia Tech, and NextFlex have all contributed to some of my photos. It's very difficult at Lockheed Martin to get stuff released, so I had to kind of rely on my outside sources to help me. And also, I don't see Dan here, but Dan Blasses helped me a lot on this presentation, told me that it was doable. So, so if you have any issues, you can go talk to him. But he's not here right now. So. He's riding around on that little bike. If you see him, that's who he is. All right. So, just a kind of a general overview here of the presentation. I'll identify a couple near-term opportunities. I tried to relate them to the RF aspects, since this is an RF related topic. So I focused on the RF portion of this. And then the challenges, they're not so much RF specific, they're kind of very general in the typical challenges you have with adopting a new technology, bringing it in, convincing, people to use it, and then actually manufacturing that product. All right, so the example I'm going to start with here is, and I might be off on my dates, I'm not sure if this is, but let's say early 90s, maybe late 80s. SMT technology, surface mount technology, was probably taking off at that time. It was a very new approach. Hey, great idea. We're going to put, surface mount parts on top of a board. We're not going to have through-hole components. We're going to save a lot of space. We're going to be able to miniaturize that. Kind of like the additive manufacturing. There's a concept of, we're going to 3D print parts and, produce things. So with that technology, though, you had challenges, right? It was kind of like a whole new way of thinking. All right, well, what do we need to do? Well, we're going to put these parts on the board. Okay, well, we have parts that have leads. So we got to take the leads off. So we got to develop that technology. Solder. Well, we need a new type of soldering process. We need to apply solder paste to a circuit board. So there's stenciling involved with that. There's companies that developed, solder pastes like Indium, or, placing the parts with Universal right down the road. That's kind of, as you develop these new technologies, that's what you have to do with this additive technology. So we have, a lot of things that you have to learn, a lot of, funding and sources of information and development that has to take place. We have to develop reliability models for the materials. We have to develop inks that can be 3D printed. There's a lot of challenges there, a lot of new things that we have to develop, and those things take time. I'll mention here too, what you want to try to find at this point is you want to find like small victories at this point. You want to find, things that you can kind of implement quickly. You don't want to completely like overhaul something because it'll never work, but you want to be able to find, little areas that you can demonstrate a performance improvement or something like that, and get your technology, like get some footing on the ground. There's also ways, I think there's companies and institutes such as like NextFlex, which we're heavily involved in, that also kind of facilitate these technologies. They, identify these gaps that I'm kind of listing here and offer funding for programs. So that's, here's a challenge, and here's how we're answering that challenge is through through institutes like that. So the next slide here, I'm going to talk about kind of one of the, let's say one of the, trying to hit one of these base hits. When I say base hits versus home runs, small victories. And this is related to inkjet printing. The benefit of the inkjet printing process is it's, very low cost. To set up a inkjet printing facility, all you need is a inkjet printer and a desk over here. So something that can be very quick and also provide very quick turnaround. Universities, obviously always have an inkjet printer. The nice thing about this for RF devices is you can do rapid prototyping. Let's say you have an antenna device and you want to kind of measure various antenna patches, sizes, and shapes. That can be done very easily using this technology. What I have shown here is, this is an example from Georgia Tech on a project. This is a inkjet printed phased array that they're working on. So it's a flexible phased array. It's designed for, let's say, like a UAV application. The idea being, if you have one tile, you can make this a multi-tile approach, and you can combine multiple of these tiles to get a better performance out of your RF device. In the center there, I have a layout of a QFN, but in the future, we hope to have it as a bare die component for bare die integration. Everything here looks pretty good, but like I mentioned before, when you have new technology, you have this idea, there's still other challenges. And the challenge with this one here in particular is, how do we actually attach a part to this device? We can inkjet print this substrate and it looks really good, and the features are very fine and everything looks good, but the ink is very thin. So it can't just solder a part to it. Solder will eat up that ink on the surface. So here we are, we have to identify, here's our challenge. We have to identify an attachment process for this particular device. So here's some options. This is how engineers work. We identify the issues and we find options. Soldering with a low temp solder is still an option. You can see here we have conductive epoxies, and the lower photos there, kind of a demonstration of applying just a conductive epoxy to pads over solder paste. The epoxy won't eat up those pads. Some of the other ideas that I really like is the use of anisotropic conductive adhesives. These are basically adhesives that if you compress them enough, they will form a connection in the z-axis and won't short from left to right for an XY direction. This is very nice because this also provides a little bit of mechanical strength to the device as well. I mentioned here again another version, another more sophisticated version of this process is developed by Sunray. This is they have a bunch of little particles in the epoxy, and the way they get their z-axis connection is they stick two magnets, on top and bottom of your substrate during cure, and the magnets actually align the metal particles in the epoxy, so that you get a connection to the z-axis. So very fancy method of doing it. And what I wanted to show here is just kind of how we have challenges, and here's how we're addressing them. The goal of something like this, obviously in the corner here in the lower left corner, is being able to attach very tiny devices, very packaged devices here. So ultimately that's the future. All right, so here's my example. I have my phased array that Georgia Tech has built. We've demonstrated it, we've constructed it, we've attached it. It's a functioning device. What's the next challenge? Well, where I work, we have probably about 50 programs running at the same time. So we're not focused on any individual program. Now we have to convince one of these program managers to, implement this technology, put this on their product. Hey, you have a UAV or you have another device. Let's use this. The challenge that comes up here is, especially in defense, is there's long acquisition cycles and long production cycles, years. It's not just it's not rapidly changing. So if you're not ready at the right time, it's very difficult. It's very difficult to bring my little phased array 3 years into a program, development and say, hey, I got this new idea, because they've already developed everything that's, pre-planned, and it's risky for them. They've already been paid what they were going to be paid and told them what they were going to do. The key here is to be very early on in the adoption. You want to be ready with your phased array, or you want to be ready with your device right at the beginning of the program. Now, this is a challenge too for someone in manufacturing, is because they don't really incorporate manufacturing until later on. And this is my pitch to anyone that's, a design engineer: get your manufacturing team involved on day one. It helps you. Every program that we have that adopts that idea works out better in the end. You'll find issues that you thought you had, or you'll run into issues later. They talk a lot about like throwing stuff over the wall. You don't want that to happen. You want to be, working together. It'll help your design engineers in the future, and it'll help your manufacturing on that product. The other thing here too is, I have this big blue text here that says every program manager would prefer to be second or third adopter. That's true. Nobody wants to be the first person. It's risky. They're scared. So there's a couple of things you can do here to avoid that. One is, if you have that technology, making sure you have all the data behind it, making sure you have reliability testing, make sure you have, figured out all the issues that you think you would have with this device. The other thing I would say too is, if you don't have someone who can be second or third, you can be the first person to adopt it. And again, I'll in my later slides, I'll talk a little bit about this, but developing your own product and actually having that available so that you can market that to these program managers. All right. Are there any, this is my next opportunity. Are there any wire bond aficionados here? Or anyone who's very into wire bonds? Raise your hand. This is going to be a little rough for you for the next couple of slides, so I apologize. Anyway, so here's an opportunity that we have been working a lot on with several companies, and I think is one of these near-term opportunities. It's getting pretty close to, I think, full implementation here. But this is using the additive manufacturing to replace the wire bonding process. So you're using essentially, we have this aerosol jet, that sprays conductive ink, and it can actually form circuit traces on a circuit board. Very fine. You can probably get down to a mil in thickness. And we have demonstrated the ability to do this as a replacement for a wire bond like device. And you can see here kind of the benefits. One of the key things too is with some of this technology, you gotta make sure you have a benefit that far exceeds the risk. So something that is very desirable. Usually where you can get that is in the performance. If you can demonstrate that performance is far superior to a conventional wire bond, that would be a huge benefit, and more program managers will be willing to take the risk if they can get, let's say, in a 5G world, at a higher frequencies, 30, 40 gigahertz frequencies, they can get better performance. They'll start to adopt these technologies. So the goals here with the performance, we believe that the conformal trace is better for signal isolation. It conforms right to the surface. You don't have this wire kind of popping off and waving around. It's much more repeatable in that aspect. And we're hoping for lower insertion loss at the higher frequencies with this device. So let's talk a little bit about this technology. And I'll kind of relate it back to, we talked about reliability and everything like that, performance, all those things got to be key here. What I'm showing here is kind of on the top, in the top left and the middle sections. These are two bare die components. One is sitting in a pocket on the left, and one of the components is sitting on the substrate surface in the center there. We've demonstrated here. If you look, you can see up in the, I can use my pointer here. You look here, this trace has been connected here using the aerosol jet printing process, and we've made connections to the substrate. On the other center one here, you can see what we did is we printed this dielectric ramp onto the device, and then we printed the conductive trace over the top of that to make the connection. I talked a little bit before about, if you want to be, if you don't have in that, everyone wants to be the second or third person to integrate a technology. Sometimes you have to make yourself the first. This is again another complement to NextFlex, where we are, designing our own phased array, full up phased array to demonstrate this type of technology. You can see there in this lower section, not only are we looking for RF performance improvements by integrating bare die onto the device. You can see here a comparison between a surface mount version of this channel versus a bare die version. You can see the components are much smaller than there. We can achieve a spacing improvement as well. As you can see, it's probably on that demonstrator unit, it doesn't really affect us that much, but as you get to higher frequencies, for phased arrays, channel spacing gets a lot tighter and tighter and tighter to the point where you can't fit everything on there. So eventually you'll have to have bare die components on there. And if you look here, this is another example of printing the interconnects between a bare die component and the substrate below. So integrating circuitry, bare die components, and using the aerosol jet print process to demonstrate that is something I think is fairly close to implementation. This is another example. Not only do we do bare die components, ICs, but we also have several different components that we're looking at. What you can see here, this is a what we call MISCAP, and it's got a little capacitor that we bond down using conductive epoxy. You can see here. And then we, again, do another ramp, print a dielectric ramp, and then we print the interconnect over the top of the device. And then you can see there in the middle the wire bonding version of this device. So we got to show performance improvement. So that's what you're seeing here. You're seeing, compared to a surface mount cap, this is performs better than that. Compared to a wire bond, it's kind of relatively the same, as you can see. But the benefit here is I don't have to, when we built this one, this is done in a clean room. It's done in usually a hybrid-like device. We're hoping to actually integrate this onto just a standard circuit card. So removing that extra step in the process is a huge benefit to using this technology. I said before too, it's risky with new technology. Well, what do we need to do? Well, we need to do reliability testing. We need to establish, confidence in this product. And one of the ways to do that is, heating it up to really hot temperatures and then freezing it to bring it down to really low temperatures, and doing that over and over and over again. Here's an example of that device that we showed before and reliability testing. You can see here that, over time that the product has not degraded. That's great. We need more information than that. That's just one chart. We want to have more. Again, here's another project that we're working on where we have several different devices, several different RF devices that have been, constructed with additive manufacturing with the aerosol jet print process. And you can see here another one in top corner up here, this guy, unfortunately, that's blocking it. So you'll have to, it looks the same on the other side of it. That's a pin diode. And what we have there is in the center, we bond down the pin diode component. And then we, instead of wire bonds, we use the aerosol jet print to connect to the top of that device. This other guy here is a coupling transformer. Again, what the neat thing here is we're able to, aerosol jet print circuit lines that go around in a coil. So the way you do that is you actually have, you print the circuit, you print the silver traces on the bottom, then you print the dielectric over it, and then you connect them from the top using the process. And that forms a coil on the device as well. So get these devices, print them, subject them to humidity testing, to thermal cycling, to thermal shock, demonstrate all the environments that you can do. Salt fog testing is another one. You want to make sure that all these devices are going to withstand the environments that you're going to be putting this through. And again, having all this data in front of you and having all this data available goes a long way convincing people that, hey, this product is worthwhile and usable for your application. Without it, if I come to them with, just saying, hey, I think this is going to work, they're going to ignore my emails. They'll probably laugh at me, but at their computers, so I won't hear them. All right. So let's say we have now, I have my, okay, perfect. I have my aerosol jet printed devices. I have my reliability data. I've demonstrated that the performance is, better than the wire bonds that used to be there. And now a program has, they've seen my work, they've seen my demonstrator, and they say, hey, we're going to use your product on our next device. Great. All right. Well, what's the next challenge? Well, now we actually have to produce it in multiple, in a production-like environment, and there's challenges there as well. We need equipment. We need, equipment in the printing area, changes very quickly. You can have we could have a machine that prints this device, and by the time we actually go to production, could be a few years down, and there could be like 4 more iterations of that machine before we even get to the point that we're actually going to start producing stuff. So it's the question is, when in a manufacturing environment, when do you actually purchase the equipment? Do you purchase it in the beginning? At the beginning of your process, do you actually, outsource it to an expert? All these questions, come up. Do you want to bring it in-house? When you're using the equipment, do you need a, person with a PhD to run it, or can you train somebody in a week how to use the machine and then have that machine run 24/7? All those challenges you have to think about when you're integrating these new technologies. The equipment or the manufacturers of that equipment, is there more than one? A lot of programs don't like to have a second source. If there's only one company that can produce that device, people get nervous, and they get, they don't want to take that risk if that company is, a small company and could potentially go out of business in, a few years' time. So a lot of things to think about. Now, for my last little opportunity here, this is the one I think is probably the most ready for prime time. And that is using this 3D printing technology to basically create conformal antennas. 3D antennas, I know in our world, it's always been a 2D. We lived in a 2D world. All of our antennas were developed through PWB manufacturing. But now we have this third dimension that we can operate in. And we have, like I said, we have multiple companies that can demonstrate this technology in different ways. So there's that elimination of that concern. There's multiple machines that can do it. It's a fairly straightforward process that can be done. The challenge here, though, is getting everybody to understand that we're capable of this technology, that this actually exists. You know, I can go to my RF engineers and they've just, like I said, they've lived in this 2D world where they've never thought about, designing in the third dimension. So our goal here is, helping them understand this technology. So that's why I'm here. So here it is for all you RF engineers. Here's a concept that if you have an idea and you want to be able to realize it, this is something that we can certainly do. So that is the end of my presentation. So thank you. Yeah, there's several companies. It's mostly silver now. It's mostly silver that we're using, and for our project, we'll be using silvers. Copper is getting close, but it's not. I don't think it's there yet. Yeah, there's a couple companies. DOA is a very good company that has a silver ink that they print. We've had some pretty good success with that. No, we have not. That'll be something that we'll have to, work on. We've coated them with just various ultra thin coatings to, protect them from the environment, but we haven't really tried to really ruggedize them. Oh, perfect. Thank you.
Yeah. All right. Thanks, Tom. Just work on getting this other one set up. So our next speaker is from UMass Lowell, Alcom Eckerslit. Close enough. Sorry about that. So she received her bachelor's degree in electrical engineering from Virginia Tech in 1994, and master's and a PhD in electrical engineering from Penn State in 96 and 2001, respectively. In 2002, she joined the Department of Electrical Engineering, Electrical and Computer Engineering at UMass Lowell. She's a full professor and deputy director of the Print Electronics Research Collaborative and co-director of the Center for Photonics, Electromagnetics, and Nanoelectronics. Her research interests are in printed electronics for RF and microwave applications, including antennas and novel electromagnetic filters, additive packaging, and the design and application of metamaterials.
Okay, good morning. Everyone can hear me okay, I guess. So I'm really happy about the speaker that came before me. So I don't need to convince you guys of using additive manufacturing because he kind of introduced a lot of the concepts. So I'm going to give an overview of all the additive, not all of it, but a majority of the thrusts we have in additive manufacturing, mostly for RF and microwave. And last night, after seeing a lot of the talks yesterday and the references to additive manufacturing, I did add a little bit more into how some of the projects we have on additive packaging. So, and my name is Alcom Eckerslit, and I have the team members that obviously this is a team effort. So everything that's here is the hard work of students, postdocs, faculty. So, whoops. Here we go. All right, so I'm going to start with an overview for a lot of you who don't really know about us. So we have a unique relationship with Raytheon. I'll discuss that. And then there was a little bit of questions about inks and materials, but in additive, from our perspective, one of the biggest hurdles to advancing additive manufacturing for any of these applications is in the materials. So I'm going to talk a little bit about some of the materials we have developed in-house for different applications. And then finally, I will go into some of this additive packaging. So I'll talk about a few projects that involve that, and then close off with some final thoughts. All right, so what is this unique model? We have, you probably saw on the title slide a bunch of different center names, but we have the Raytheon UMass Lowell Research Institute. So it's a co-location model. It was set up in 2014. So we actually have Raytheon employees on site. They work day and day with us. It's not like they just give us money and then we report to them. So we have lots of projects that we do together. There are permanent employees that are at UMass Lowell every single day. And of course, so we also go into CRAD opportunities together. You see on the left some of our federal funding that we've gone together with Raytheon as well as on our own. And the other aspect of this model is the talent acquisition. And I know yesterday during the panel, there was a lot of discussion on workforce development. And I think these kinds of models are important in really relaying this information and then attracting students to places like Raytheon instead of like Google and Facebook, which we're always, we were talking about that yesterday as well. Now, when we set this up, in order to really build the ecosystem, we ended up setting up another center called the Printed Electronics Research Collaborative, which allowed us to really build out our research space. And I'll show you guys some pictures of our labs. And this is a consortium of currently 19 companies, and we have different relationships with all of them. It could be SIBRs, it could be other projects, it could be exchange of materials like we do with Creative Materials, which is a small company nearby. So that's, and we really think of us as sort of the R&D for printed and additive manufacturing electronics for Raytheon in applications with RF and microwave. So we kind of go through the entire, design process. All of our students know how to do electromagnetics design, et cetera. Then, of course, we go in, we do the printing, the materials development, characterization, that's critical. I'm not going to go into some of our printed RF devices like antennas and things like that, but I can talk about it later. You see a few pictures here of a Vivaldi antenna that was 3D printed. Printed connectors, I'm going to touch upon that towards the end. Microelectronic packaging, what we've been doing in that area, printed metasurfaces, and then some, just a synopsis of some work that we're doing for authentication. So using additive in that area, which is something that hasn't really been mentioned, but that's also very important. Again, within Rovere and PERC, we go through the entire process. I'll kind of skip through this. So these are some of the equipment that we have. So we do have the Optimec 5-axis. The speaker beforehand talked about, this gives you that additional 3-dimensional ability to print on 3D objects like concave and convex objects. And I'll show you some videos of some of the work that we've done. We have a Hyrel, which is kind of a cheaper version of the Enscript, and we have the Enscript forehead. And I'll show you how we use that. There's a lot of different ways that we've utilized that. The Nordson, that's a really simple one, but it's very useful. We do have a pad printer that a lot of people do not have. This is a very interesting technology that we're hoping allows for scale up. And then we have various 3D printers. And we have more nice things coming. So, and then the characterization lab. So as I mentioned, we want to obviously measure, and look at the RF performance, but we also have a huge thrust in material characterization, electrical material characterization. So dielectric constant, loss tangent, up to like 50 gigahertz for a lot of the inks that we develop, and also ones that we get from companies, because a lot of times they'll give you these numbers at like 2 kilohertz, which doesn't really help us. We also have an anechoic chamber. And so we can also do some thermal testing, but a lot of our like thermal analysis will do it at Raytheon. So because we're also very close geographically. I probably should have mentioned that. All right, so again, really for those of you who have been involved in additive manufacturing, as I mentioned before, materials is really the key for advancement. We take for granted a lot of materials like copper and low loss dielectrics. When you go into actually printing these, obviously there's materials with different viscosities that are for different printers, but you got to worry about the different material characterizations. And within our lab, we have a huge thrust, and I'll initially talk to you guys about the novel materials that we've developed. And they pretty much tie into all of the projects that are shown here, anything from additive packaging, technology protection, antennas, printed textiles. So any additive work. All right, so one of the first inks that we developed was a BST-based ink. This was so we could make printed varactors. As anyone who knows about BST, it's a ferroelectric. So if you apply a bias, the dielectric constant changes. And so it's used a lot in the microwave world, but it's a ceramic that has very high sintering temperatures. So if we wanted to print this and print it on a flexible substrate, well, obviously then we can't really sinter at those high temperatures. So instead we made a BST ink utilizing BST nanoparticles. And we were able to obtain, we can vary the dielectric constant, the real part, and we can get anywhere from like 6 to up to 50. So it can be used not only as a ferroelectric ink, but also as a high K ink. So for antenna miniaturization and things like that. We've also demonstrated tunability at 10 gigahertz, somewhere between 10 to 12%. And our losses are within the 10 to the -3 regime up to about 12 gigahertz. Where did we use this? So this was a project, one of our earliest projects with Raytheon, where we wanted to go from a rigid FSS structure that had surface mounted reactors and make it fully printable and on a flexible substrate. So what you see in the middle is the FSS structure that's tunable, that's capped on. It's actually printed on both sides. It's the design is a metamaterial design that's actually less prone to angle of incidence, so you can get a fairly good performance even when you're bending it. What you're seeing I'm pointing to it with the arrow, that's a printed varactor, which is essentially a printed IDC, interdigitated capacitor, with the BST ink. So if you apply a bias to that ink, it changes the dielectric constant, and therefore it changes the capacitance. So here's a picture, and you guys might have seen this picture, anyone in the additive world. This picture is used a lot in like different papers. You can see the dynamic tuning for this FSS structure using the BST-based varactor. All right, another key area for anyone in additive is really developing low loss dielectric inks that we can actually print. So we have been working very recently on variable viscosity, solvent-free, low loss dielectric that can be printed with using the aerosol jet, so you can get very thin lines, and then also using other printers like, let's say, microdispensing, Nordson and things like that. It is UV curable, but it's also can be used via the thermal curing as well. So far, we've made measurements up to 18 gigahertz, and we're within the 10 to the -3, which is an order of magnitude better than the commercial inks out there. And so far, we've had outsiders try it as well. So LPS has printed it on their aerosol jet system. And next month, it's going to travel to AFRL and to see what we can get there and try to get more usage out of this ink, so we can also figure out what's wrong with it and make it better. As we were working on some other UV curable inks, one of the students, as he was printing on our aerosol jet, realized that based on some of the print parameters he was using, he was actually getting a 3-dimensional stack up. So this is utilizing only the 2D stage. But as you can see in the video, hopefully it's clear, we decided to print a flower because it was pretty, and you could also demonstrate sort of that freestanding, each of the petals. And so this is, I love this slide. I just think it's really nice. And so it can show you that with material properties and then the optimization of the print parameters, you can get some really interesting structures as well. Again, just utilizing 2D. Another ink that we have was actually developed by one of our faculty members, Dr. Ash Ranasinghe, who's here. So resistive inks is also another area that needs more research when you're going into printable electronics. So the idea here is taking conducting ink, so the commercial silver ink, and then actually putting BST nanoparticles in it, and to make it more resistive, essentially. So this is called the AGBST ink. The beauty is when you put it on, it's an insulator. But then when you either thermally cure it, or you can actually go in and laser sinter it. So what you see on the top right, so you can get very thin lines using laser sintering. So whatever I write turns into a resistor. And so on the bottom, you can see we made IDCs utilizing this AGBST and the laser sintering. And we can also use, so we have the 830 nanometer that's on the aerosol jet printer that we have, and then the 405 nanometer we have in our clean room. So this is a very, and we've actually also developed additional UV curable inks that can be printed on top of it. So it then stops changing even if you apply heat to it. And we have patents on this and a paper, we have a paper on this as well as on the UV ink that has just been accepted. So we can share that with anyone that's interested. Okay, so I wanted to, these are some of the additional slides that I put in after yesterday. So this is a project that we have with Raytheon that's funded by NextFlex. And the idea is really to look at how we can use additive manufacturing for circuit compaction. And so one of the, we had a previous project, again, funded by NextFlex and with Crane in making these printed interposers. So the interposer that you see on the left, that is printed out of PEEK. And I'll go through the details of the lines over them, but you can also see for reference the size with respect to the dime. The cartoon that you see on the right is essentially the test bed that we're using to utilize the advantages for additive. In this case, we have two mimics, and I should have said that the PEEK interposer is, near chip size. So the idea is that the interposer sits on top of the mimic. We have the conducting traces that form the DC connection, but when you put it into the PCB, then we have a gasket ink that fills the gaps, and that's also an in-house developed ink, and I'll show you a few slides that go through that a little bit more. And then this also allows us to demonstrate isolation because we've got the two chips in this test bed. All right, so I wanted to show you guys this video. This is actually showing the interposer that actually has a planarizing UV ink on it. That's that white that you kind of see. I haven't hit start yet. This is inside of our Optimec 5-axis system. So it's in the holder. Let me show you where it is once it starts moving. So this is the interposer right here. It's in a holder, and I'll talk a little bit about the holder in the next slide. And so now let me hit go. It was supposed to play automatically, but all right. So everyone can see the interposer in the holder. So that holder actually has a heating element because as you can see, this thing is flopping around. And as it was doing that, when we initially put it in there, the ink was kind of flying all over the place. So it has a heating element that heats it just enough so that ink settles into place. And then we're printing these conducting traces. This is all commercial inks, the conducting traces, but as you can see, it actually wraps around under the feet as well. So, and you saw the dimensions of this interposer. So again, the former speaker talked about this as well. There's a lot of capabilities that you can get with these advancements in the printers. All right, so this was just to show you guys, I wanted to include this. It's a busy slide, but I just show you guys that interposer like, hey, it's done. but it's a huge process. And again, this is a new technology. So there are a lot of different things that go in. So initially looking at which conductive inks to use, we don't develop our own conductive inks. So it's all commercial. You got to consider the conductivity. You got to consider adhesion. You got to consider mechanical robustness. The fixture design, I mentioned that already. That's to go into, that's the holder for the interposer within the 5-axis. The whole printing process. And then we've also developed repair processes, because sometimes you're done with everything. There's that one little spot that's missing. We can go back in and do that. And then planarizing. So another issue with 3D printed parts is the surface roughness. So the best way we got around it was, again, an in-house developed UV ink for planarizing and then printing the conducting traces over it. So lots of steps, because it is a very new area for these applications. Now, in order to test these interposers, we then put them into a printed circuit board. So stage 1, there's no interposer. Stage 2, the interposer goes on. But what you note is then we put the gasket ink around it, because there's spacing around it. And then we have to print the conducting traces over to the interposer, which is what you see here. Now for that, we actually used our end script, because we needed to use some other more mechanically robust inks, and those are higher viscosity, so we can't use them in the aerosol jet. Aerosol jet requires less than 1,000 centipoise for the inks. So, and here's a close-up of what that looks like. So we use a laser detector to get the topography. So I have an image on the left, and then we're able to get these prints across the printed circuit board to the intercorrect. And I just kind of put in, we looked at, and these also have gone through thermal cycles. So we looked at obviously continuity, isolation, and these look really nice. I'm not showing our first efforts, all right? So now the previous talk discussed direct write interconnects, which I'm happy about, because then I can just dive right into it. We've been looking at integrating bare die, just as everyone else is. And so I'm just going to present a little study that was done on like pocket bonded versus direct bonded. So I think the speaker before me showed more of the direct bonded, where you print dielectric around the bare die, and then it's a ramp, and you actually go up the ramp to the chip. There's also another one, which we call pocket bonded, where you can create a little housing for it, put the chip in, you have some conducting epoxy, and then you can you fill around the gaps, but you don't necessarily have a ramp, and then you just print the conducting lines directly through. And so this is some attenuator chips. So we start with the cheap attenuator chips that we can, get rid of if things don't work. So you can see pictures of what pocket bonded and direct bonded bare die chips look like. And then these were some initial results that we got, which showed that the pocket bonding got better results. Even though this might be the case, there are certain cases where, due to the geometry of the problem, we might end up still going with the direct bonding. So this is a more complicated die. This is an LNA from Analog Devices. And I actually have a video that shows all the steps. Sorry, that went fast. I tried to shorten it last night because it's, so we start with essentially our LPKF laser miller to go through the PCB. And then we're using right now, what you're seeing is our end script has a pick and place. So it's picking up the die. I know it's a little slow. I wanted to speed it up, but I couldn't. So bear with me. So there's your LNA, and it's going to move over to its housing. Again, this is all done with the end script that I mentioned before. So we're using multiple printers for this process. And so there it is. There's already some epoxy there. So, and then the next step is the chip. Now you can see is on the coupon. And so then we do the actual dielectric around the chip so that fillet or ramp and that's syringe dispensed. And we can also do aerosol jetting or NScript. And then we use the UV cure on the Optimec. And then that's what it looks like after it's UV cured. And then we're doing the conducting printing on our Optimec to the chip. So these are the transmission lines to the chip. All right, let's see. Oops. Here we go. All right, so now switching over to some work that we've been doing with AFOA and a small company out of Cambridge called Notch. And we are doing printed metasurfaces onto fabric for anti-jamming and Wi-Fi boosting applications. So we've demonstrated that utilizing these metasurfaces, we can actually, get rid of the jamming signals, filter them out. So what you're seeing in the middle is the Nordson printer printing the metasurfaces. This is a stop band metasurface. We have also different designs that have, the dual sides. On the bottom left, you see our free space measurement system for looking at the RF performance. And then on the right, you see the system in our anechoic chamber. And it is because we've demonstrated interesting Wi-Fi boosting with antennas in the presence of these metasurfaces. All right, and one of the final parts that I'm going to discuss is printed connectors. So the previous speaker also showed phased array antennas that are printed on nice flexible surfaces, but then at the end of the day, you stick a rigid connector and then you kind of, defeat the purpose of having this really nice, flexible, conformable structure. Another thing is because of the size, we can limit the density of the signals. And so what we've been working on actually with Kansas City NSC is looking at redesigning the connector. So we're looking at like planar design, which is essentially overlapped CPW lines. And also what we're looking at is different types of signals. So you can have a DC as well as an RF signal on the same connector. And then we have holders that are mechanical holders for these planar structures. And so in the next slide, these are some peak printed parts. So on the left, you can see the two parts before they came together along with the mechanical holders. In the middle, you can see the final connector and you're gonna say, well, there's connectors on this. Well, that's just for the testing. So to demonstrate the RF performance. And then you can see on the right where the connector is going to be connected to another circuit that is on the peak. And so we were able to demonstrate this. Right now, we're looking at some flexible connectors that we can work with KC. And so far, we've gotten some initial good performance, but up to about 6 gigahertz. And we definitely need to improve those performance for the higher frequencies. And then finally, I mentioned a little bit about AM protection. Unfortunately, we can't really show you guys any slides on this except for this one. But we utilize the advantages of additive, which is that it is so random. So there's a lot of questions about repeatability. Sometimes not having repeatability is a good thing. And so in the area of authentication, that's definitely a good thing because we're always trying to create these physically unclonable functions. And we're also utilizing the fact that we have these novel inks. And then you can also look at different stimuli, including like voltage and temperature. So we've done several different test beds. Unfortunately, I can't really show them, but I showed a simple like barcode. It's a thermal IR signature of it. And then we've also printed on like parts of circuits. And that was also with Raytheon and another company called Microsystems. So there's a lot of places where you can utilize additive. And hopefully I made that point come across. Final thoughts, as I was watching the former talk, the previous talk, I thought about a really nice line I saw from Dan Hines's talks a few months ago, which is print what you can and place what you can't. And I think that's really a great message. And I should have put that on my final thoughts, I thought. But So, this is kind of a summary, but at the end of the day, I hope I made it, some points come across that there's a lot of potential in additive. There are also a lot of challenges, especially with materials. And so that is, hold on, this is the team. And so faculty, staff, and students, and as well as the Raytheon team that we work very closely with. So thank you for your attention. Once you have the AGBST on, right? So that's an insulator. And then when you laser sinter, what happens is that you end up creating little lines of the AG. So they end up coalescing. So that's how you end up getting some conductivity through that. Then we don't wash anything away. The other parts are insulating. Only the parts that we write end up being conducting. So we don't need to wash away anything. Sure. Sure. It's like a Lego. So it kind of snaps on. Yep, it's a snap on. So I really like to refer to it as like the Lego connector. And we had to put, because it was moving, we did have to put those additional little things that I showed in the slide that kind of hold it in place. Yeah. All right, thank you.